Good morning, everyone. I would like to begin by acknowledging that Concordia University is located on unceded Indigenous lands. The Kanien'kehá:ka Nation is recognized as the custodians of the lands and water on which we gather today. Montreal is historically known as a gathering place for many First Nations. Today, it is home to a diverse population of Indigenous and other peoples. We respect the continued connections with the past, present, and future in our ongoing relationships with Indigenous and other peoples within the Montreal community. I would now like to introduce our first speakers, Drs. Christophe Grova and Karen Lee.
Thank you, Wendy. So as Christophe is getting slides up, I see they're up. I just want to thank you for the opportunity to present today. And so we are very excited about our invited keynote speaker, Dr. Meltem Izzetoglu. But before her talk later on this morning, together with Christophe Grova, I have the pleasure of presenting some of the work that we've done and plan to do in a new collaboration at Perform. So as you can already surmise from the title of our talk, our project involves neuroimaging, aging, and walking. So I want to provide everyone with a bit of background and hopefully tell the story of how we came to collaborate. So here in Canada, we passed an important milestone in 2016 in that the proportion of seniors exceeded the proportion of children in the overall population. This underscores the importance of maintaining good physical and brain health, adding life to our years, and maintaining functional independence. Put a different way, we want to find ways to maximize functional capacity for as many years as possible. So in the lower right graph, you'll see following the upper function is sort of the ideal outcome, maximizing the functional capacity for as many years as possible, and conversely avoiding the disability threshold below which significant assistance is necessary. So in geriatrics, functional capacity can be defined as activities of daily living. Each of the photos depicts a type of ADL, activities of daily living, and instrumental ADLs, which have been shown to correlate with cognitive processes and specifically executive functions such as switching, inhibition, and planning. Importantly, if you look at each of those photos, each ADL involves the coordination of sensory motor processes and cognition to plan, attend, remember, and so on while the body is in motion. In other words, we're constantly multitasking. Next slide. So borrowing from cognitive psychology, gait and posture researchers have generated a large body of work to date on motor dual tasking, what we have called cognitive motor dual tasking, or CMDT for short. In healthy aging, the addition of a cognitive load, such as conversing, listening, remembering, navigating, and so on, all of these cognitive activities reliably disrupt walking in older adults. And this disruption, or dual task cost, is exacerbated with postural threat or with neuropathology of different sorts. Finally, researchers have further argued and shown evidence that this type of complex walking is a sensitive predictor of falls, a predictor of cognitive impairment, and not surprisingly, a predictor of poor mobility outcomes. Next slide. Why would cognitive load impinge on something that we consider to be largely motoric? Well, some early studies of structural neuroimaging of the aging brain suggest a greater reliance on brain structures we normally associate with cognitive functions, and specifically cognitive control or executive functions. In two large-scale studies from Katerina Rosano's group at UPittsburgh, one in the cardiovascular health study, usual walking speed was associated with individual differences in prefrontal and cerebellar volumes, and with white matter integrity in those frontal anterior regions. The second example comes from the Healthy Brain Project, and their usual walking speed was associated with white matter hyperintensities, which is an index of lesion burden. And where this was found was in anterior thalamic radiation and the anterior corpus callosum. So the interpretation of this is the connection between thalamic nuclei, which we know are quite key to motor initiation and motor control, connecting that to frontal regions. They found that there was an association between gait speed, but this was also mediated by neuropsychological measures of executive function and processing speed. So again, this implication of cognition comes out in the analysis. There was a direct association found between anterior corpus callosum associated with usual gait speed, suggesting that the communication between hemispheres is important there in the anterior regions. So that's a very brief and selected summary to address that question of why it is that cognition should be associated in old age with mobility. However, these correlational studies are just that. So directionality of conclusions is limited. Instead, in my lab, we've used more experimental techniques to get at the same question. And I note that today, our keynote speaker will fill us in on the state of knowledge regarding functional neuroimaging and gait, which is her area of expertise. So in my lab, the strategy that we've taken has been to experimentally increase the efficiency of these prefrontal circuits and to test for benefits in mobility tests like the dual task walking or other mobility tasks. We design our training interventions to target cognitive functions that are supported by prefrontal circuits. So you see those on the left that have some overlap with the regions implicated in older adults walking. So the most focused, and I would argue the most pure kind of experimental manipulation and test of this cognitive hypothesis is cognitive training that is done in a seated manner with computerized training programs. Second, we've got aerobic exercise and resistance training, and they're also known to effectively improve cognitive control functions. So I list some of those examples, but then at the bottom, you'll see some maybe less conventional training interventions that we have used in my group. Cooking training is an interesting one. It's a very multifaceted activity that was introduced by a postdoc of mine who's an occupational therapist, Frédéric Pensée. So this involves object manipulation, planning, memory, organization, monitoring, changes in center of pressure as you reach for objects and you lift things and manipulate them. Finally, multi-object tracking. This is a very new endeavor for us, but multi-object tracking is a bit like a computer game, and it entails following objects that move around on a computer screen amidst other objects that are non-targets. And so this, we think, is going to help to improve dynamic visual attention, which is something that we employ when we walk in a busy environment and perhaps need to avoid moving obstacles such as other pedestrians on the sidewalk. So on the right, the mobility outcomes you'll see are varied, but we always test the motor performance under full attention and also under concurrent cognitive load in order to mimic multitasking. So next, I'm going to show you a couple of examples to illustrate just very briefly. In this first example, that was led by Helena Bruce and Lawrence Lai in my lab, we tested if multitask training might be more effective than sequentially training cognition and exercise. And so this was given that our major outcome measures involve cognitive motor dual tasking. So the logic was maybe if we train people to do these things simultaneously, that will be more effective. So Helena and Lawrence assigned healthy older adults to one of two training formats, simultaneous or sequential. So the simultaneous group cycled while doing their dual task training on iPads. And the second group did their iPad training first, and then they got on the bikes and did an equal number of minutes of cycling. So our major outcomes were the dual task clinical test of mobility called sit to stand, which is rising from a chair 5 times as fast as possible. And we added one back working memory task, which is a task of memory updating, listening to digits. So we had people tested singly and then together under dual task conditions. And here we also manipulated sensory challenge to see if either training format was particularly beneficial in poor listening conditions. So on some of those NBAC trials, we turned the volume down below ideal listening levels. And so this is part of a larger project. We've taken on the question of the known link between poor hearing and mobility based on evidence that having age-related hearing impairment increases the risk of falling by 3 times. So the question, a secondary question, was whether those who are hard of hearing might benefit from this kind of intervention. So very quickly, the diagram to show the design more formally, but I won't dwell on this, only to say that, we did the standard recruitment and screening and one set of pre-training assessment of a variety of cognitive measures, and then also those single and dual task tests of mobility. And then people were randomized to 6 weeks, 2 sessions per week at the Perform Center, doing either simultaneous or sequential training, followed by a repeat of the assessment battery at post. So on to the data. So what I'm showing first is the auditory working memory task data, and complexity increases from left to right, starting with the seated single ideal listening, all the way to doing the one back task in poor listening conditions during the sit to stand. So that's labeled as dual low. And what you can see is that the sequential training format really wins out very clearly here. So that format led to substantial training gains, whereas those randomized to the simultaneous training group did not show such gains in the cognitive performance. We originally thought that simultaneous training might be advantageous, but with 2020 hindsight, we interpret this as it makes more sense to train both components under full attention rather than divided attention. So now looking at the motor performance below, and you see the illustration of the 5 times sit to stand test, we found that both training formats benefited performance in the most complex condition, although again, sequential performance was superior. Now, importantly, our cognitive outcomes from this study suggest that older adults with hearing loss benefited the most from the training overall. Thus, in the next example I'll show, it's ongoing work, so very preliminary evidence, but it illustrates how we have designed an intervention study that includes older adults with normal hearing and then an older group of experienced hearing aid users. So this is work that's been led by my PhD student, Rachel Downey. And in this design, we also added a group of middle-aged adults, knowing that hearing loss begins in midlife and that a recent Lancet paper identified midlife hearing loss as the leading modifiable risk factor for all-cause dementia in later life. So we really think more research needs to go into this middle-aged group. So with this study, we're concentrating on cognitive training only, so there's no exercise training component, but we use the kind of standard program that we have developed in collaboration with Dr. Louis Barrère that trains specific executive functions such as working memory, inhibition, and dual tasking. So this is done at home. It's delivered over the internet, and we have doubled the training duration to 12 weeks now, and we have people doing their training 3 times a week at home. So this design is a waitlist control design. So our participants either logged into the training program 3 times per week or did not receive access to the training program until the conclusion of the study. regardless of randomization, everyone was contacted once a week, just as a telephone check-in to see if there are any adverse events or queries. So the pre and post training assessments are similar to the previous example study, but I just want to highlight some key differences showing on the next slide. So our key outcome of concern here is cognitive motor dual tasking, that's CMDT. And here we are operationalizing CMDT as dual task treadmill walking, with the cognitive load being a 2-back working memory task. And this is presented at ideal listening conditions and corrected individually depending on each person's hearing ability. So here is our setup in the posture and movement lab at Perform. Some of you will be familiar with this room in the basement of Perform. And importantly, in addition to having the standard conditions of single task walking, single task cognition, and dual task walking plus cognition, we've added functional near infrared spectroscopy, which you'll hear a whole lot more about in Christophe's section and in the keynote talk. So we added this to the pre and post training assessments to test for evidence of neuroplasticity in prefrontal cortex. And so because this is just ongoing research, I'm just only able to show data from the training phase from our first cohort. And we're about, I think, a little over halfway done with data collection, but we should be done by the end of this year. So here, what's showing is the training phase data on those 3 executive function tasks that we gave people to do online at home. And we just first wanted to demonstrate that the training actually did lead to improvements on the trained task. So we've got contrasting session 1 performance against session 23 performance, so at the end of 12 weeks. And so the graphs are divided between the different training tasks. The y-axis is reaction time, so low numbers indicate faster responses. And on the x-axis, we have different conditions within each task with a level of complexity increasing from left to right. So overall, what we found was that the reaction time significantly decreased across all of the training tasks between session 1 and session 23. That is, they all became faster. So that's good. We also found a time by condition interaction in most of our task analyses, such that there was greater improvement in the reaction times for the more cognitively demanding conditions. So in NBAC, we see greater improvements in the dual mixed, and in working memory, we see it in the 3-back, the most challenging condition, not so much in the 1-back, which is easier. So based on these results, we can pretty confidently move forward and conclude that the training program does target the executive functions, and it's not just a matter of people getting faster overall. So we then created change scores contrasting the session 1 and session 23 numbers. And so in the next slide, you'll see how we address the question of whether individuals with hearing impairment benefit more from cognitive training. So in this graph, we use the pure tone audiometry, which is a standard clinical test of hearing acuity. And going from left to right on the x-axis, to the right is worse hearing acuity. That's decibels that are needed, the amount of sound energy needed to actually detect the tones. And then the change scores are on the y-axis. So the larger improvements are shown in terms of a reduction of reaction time in milliseconds. So the lower the value, the bigger the improvement. And here, even with just our cohort 1 data, we were able to find significant relationship between hearing acuity and the magnitude of cognitive change through training. So we find this very encouraging. As mentioned, I'm only able to present some preliminary results because our study is underway, but I hope that I've given you a sense of the type of work we've done at Perform on the topic of cognitive motor dual tasking and how we're starting to incorporate fNIRS acquisition into our designs in order to substantiate what we hypothesize to be the cognitive and neural underpinnings of training-related improvements to mobility and multitasking. So with that, I'm going to turn the floor over to Christophe, who's going to elaborate on his team's work with fNIRS and some of our new collaborative work. Christophe.
Okay. Good morning, everyone. I hope you hear me well. So it's my pleasure to be here. And thanks, Karen, for the first part of our presentations. So now my role is to show how fNIRS, so functional near-infrared spectroscopy, is a new emerging wearable imaging technique that can be nicely used in the context proposed by Karen. So I will first go over the basics of fNIRS, show what kind of methodology we developed in the lab, to then introduce how we are now applying such methodology in the context of the research provided by Karen on aging and multitasking. So the basic principle of fNIRS is to shine light on the brain. So it's basically the same principle as pulse oximetry, where you put a laser source on your finger and you see red light coming out of it. And the amount of red light coming out is going to be sensitive to the amount of oxygen you have in your blood locally. So that's what we do from the scalp to measure blood oxygenation in the brain. So fNIRS is very interesting in our context here of dual tasking because it's a wearable technique. So it can be used while walking on a treadmill, which is not the case, for instance, for fMRI. And it's non-invasive, and it can measure two aspects of hemodynamic, which are oxy and deoxyhemoglobin, and with great temporal resolution of, let's say, 10 Hertz to almost 100 Hertz, so quite rapidly. So how does it work? We place a source on the brain, so a laser or an emitting LED. We emit near-infrared light. And then light is scattering, so it's diffusing everywhere. It's changed direction all the time when it goes in the brain. It does not go straight like X-ray typically. So it means that if you put another detector away from that, typically 3 centimeters, some light will scatter in all directions and some light will go back there to that detector. So you are measuring the light that travel this path with a very scattering profile. And so the light is following what we call a banana shape between the source and detectors. The magic number is roughly 3 centimeters between source and detectors, allowing us to explore more or less 1 centimeter depth of cortex. And so the bottom of that banana could reach the cortex. So what's happening now if you have local brain activity changing? So if we have local brain activity, like what we measure in fMRI, typically what will happen is you're going to have local change in hemoglobin content, and this hemoglobin will absorb the light. And if hemoglobin concentration change, light intensity will change, and this is what we're going to monitor. And why near infrared is because in the near infrared optical window here between 650 to 900 nanometer, what we see here is we have very little absorption from water, which is very good for us since most of our tissue are made with water. And we have two interesting chromophores here, which are oxy and deoxyhemoglobin, and the two absorption spectra are getting inverted. So by using two wavelengths, one more sensitive to oxy, the other more to deoxyhemoglobin, with a little bit of equations, we can retrieve what the local relative concentration change in oxy and deoxyhemoglobin. That's the principle of fNIRS. So we're able to monitor slow hemodynamic response elicited by a neuronal activity. This is what we call the neurovascular coupling. So a typical response, if I have a task here, would be a large increase in oxyhemoglobin, an increase in total hemoglobin, and a decrease in deoxyhemoglobin, peaking roughly 5 seconds after the beginning of time. So this is what we call the neurovascular coupling. It's a combination of two sources. First, as for bold fMRI that was introduced by Dr. Gauthier yesterday. So we're measuring the same kind of activity. First, we have local consumption of oxygen, so increase of oxygen metabolism. So that means we're going to extract oxygen from hemoglobin. So we're going to have increase of deoxyhemoglobin, decrease of oxyhemoglobin. But more than that, we have the neurovascular response, which going to result in very large increase of local cerebral blood flow and dilation of small arteries. And since we have a large increase of blood flow, we're going to bring lots of fresh bloods, and this is going to rush out all the deoxyhemoglobin. So we have a huge increase in oxyhemoglobin and a small decrease in deoxyhemoglobin. And this is why we result with an increased oxy and a decreased deoxyhemoglobin, which is our main expected measures. The one aspect, one complexity of fNIRS is when, of course, we would like to measure brain cortical signals that are elicited by neurovascular activity through this neurovascular coupling principle. But we're not sensitive to that. First, light is traveling through the skull, so it's crossing different layers before reaching the brain. So we're also sensitive to some extracerebral layers, so absorption in the skin, in the water. We're also sensitive to non-evoked fluctuation, like ongoing oscillations, like respiratory, for instance, and we are sensitive to systemic fluctuation. So change in cardiac pulse, respiratory, arterial pressure will be seen in our data. So we have to cope with all those techniques. And this is nicely summarized in this best practice paper published last year. So we have techniques trying to improve our quantification properties of fNIRS data. One idea is not to use one source and detectors, but rather an array, and ideally an array containing different distance between source and detector, so to be sensitive to the different layers. Of course, we can deal with like the skull thickness is an issue, so smaller one is better. That's why fNIRS has been used a lot in infants. And ideally, we would prefer to measure systemic physiology, like using cardiac rhythm, respiratory belt, and to correct for physiological noise, like those systematic noise. And finally, I'm going to talk about that. 3D image reconstruction is also a technique to try to improve the accuracy of it. So this is just a basic example in the early days in my lab. So this was during a standard finger tapping task of the right hand, like a task like that, and a typical block design. And this is the kind of montage we attach on a EEG cap with the light sources in red and the detector in green here. And the result here, the same subject went to fMRI and then NIRS, and you see a typical contralateral increase in bold fMRI, which corresponds to an increase in fNIRS oxyhemoglobin and decrease deoxyhemoglobin. We also have an ipsilateral decrease, which might be inhibition. So, of course, the main advantage of fNIRS is not the spatial information, which is lower than fMRI, but it is portable. And the other thing, it has a great temporal resolution, like typically around 10 or 20 hertz here. So here you see the detail of our measures of the relative of the time course of those responses. These are for contralateral sensors where you see clearly a positive response with increased oxy, decreased deoxyhemoglobin, and an ipsilateral negative response with a decreased oxyhemoglobin and an increased deoxy. But fNIRS is not only that. Like there are several complex aspects when dealing with fNIRS, and even more when dealing with, I would say, wireless fNIRS when you want to study dual task. First of all, where do we place our sensors? As opposed to EEG, there are still no standard procedure or standard cap to install sensors on the head of our participants. Several technologies, like shown here, have been proposed. It might be difficult to assess where are the area that are illuminated, that are explored by those caps. It might be difficult to maintain the contact during prolonged period when you want to do long recording or recording emotions. And sometimes you want to integrate those measures with EEG. So we have the standard 1020 EEG, and we want to have strict 3 centimeter distance for source and detectors in this, which might be problematic. So what we developed in our lab, we first developed a technique to solve that issue. And what we propose is we propose what we call a personalized optimal montage. So how to ensure that our target brain regions will be well illuminated. As Karen was showing in dual tasks, like prefrontal cortex is one of these typical targets. So we propose a methodology to find the best position of the fNIRS sensors to reach a specific region. So this is how it works. We have a set of possible position. As you see a lot in my lab, we are just gluing the sensors on the head. So we're not using cap, or we can use a cap and we can use the same algorithm to optimize the position of the sensors among the discrete position in the cap. So then we are building a head model. See here, T1 MRI with the different tissues layers. And then for a pair of source and detectors, we can use Monte Carlo techniques to simulate the propagation of light intensity within that specific head model. So then if we want to reach a specific regions, like here the motor cortex, we can look for all the specific position of source and detectors that are maximizing the sensitivity to this presumed region. This is not an easy mathematical problem. This is what you call an optimization in integer number. And we used a linear programming technique implemented in IBM software to solve that. So the resulting, the output of algorithm is a set of source and detectors that are nicely aligned to cover our target regions. It could be here it's the motor cortex, it could be the prefrontal cortex, and so on. And now to do very accurate recording during long time, we use a neural navigator to place them on the head of those participants, and we are gluing them using collodion. As for prolonged EEG recording in clinic, people are using that kind of adhesive as well. Here is a set of possible montage to target some specific regions. It's working quite well, and moreover, what can be done on that is not only this algorithm allows you to make sure you're going to be highly sensitive to this particular brain region of interest, because you want to have an hypothesis that you want to study very accurately this brain region or these different brain regions. And then what's going on here, you see a different set of source and detectors. So we have spatial overlap. So we have different techniques, different measures, which we might not have in a standard fNIRS montage where we have a strict 3 centimeter distance between source and detectors. So this spatial overlap allows us to do something else, which is local 3D reconstruction. So this is a little bit, this is my only equation for today, a little bit like what we do when we do EEG source reconstruction. We have our fNIRS signal that are on the scalp. We have what we call a forward model, which is how light is propagating within the different layers of our tissues. And then our goal is to recover what are the local change in oxy and deoxyhemoglobin along the cortical surface from the signal we are measuring from the scalp. So in a way, what we are proposing here in this context is really to develop 3D reconstruction, so 3D imaging from fNIRS, and we develop a specific technique called maximum entropy on the knee. So this is the work of Zhengshen Kai. He did a very nice work here. So this is the first study that was done on realistic simulation. So he was placing some artificial generators over the cortex. He put an hemodynamic response, added real background noise, and then applied the reconstruction. So here the truth of our different source is what we see in black, and you have the result of our algorithm. The first two columns, our algorithm, the last two, the standard algorithm from the literature, the minimum norm estimate. So we are outperforming the standards. And this is the same technique now applied on real data. So in this data, we apply this analysis to study the motor cortex of 10 healthy controls who underwent finger tapping in fMRI and then in NIRS, targeting the right hand knob, proposing our optimal montage here, targeting that regions. And this is the way we set up the optodes. And this is the result on our 10 subject, where you see for each map, the fMRI map for the finger tapping, the oxy and deoxy hemoglobin response for our method, and the standard method. And as you can see here, we get very nice results, highly similar to what you get with fMRI. And this is what you get at the group level. Not strictly similar, but very, very interesting and complementary to fMRI, since fMRI cannot disentangle oxy and deoxyhemoglobin, and we have the time course of those responses. So now let's move to how we would like to apply this kind of methodology in our context of doing dual task. So this is the first study. This is a grant Karen and I got from a multidisciplinary multidisciplinary research proposal in preventing health. So the idea was to study dual tasks. So typically here it's arithmetic tasks, so subtracting the number 7 while walking on a treadmill in younger and healthier adults and older adults. And we put a whole multimodal platform that's designed here. That was the master project of Amanda Spilking. So we have personalized NIRS, so wired NIRS targeting bilaterally the prefrontal cortex. Then we add wireless electromyography to follow the muscle of the legs while walking, foot switch for gait measures, and we have monitoring of motions using accelerometer. And unfortunately, we were stopped during the acquisitions because of COVID, and we are restarting now. So here you have one preliminary results where you see the setup. So this is targeting bilateral prefrontal cortex, the montage with wired. So you see our NIRS system with wired. The participant is on a treadmill with EMG, a safety harness, and now is going to walk and do the serial 7 subtraction. And this is the first result of one of the comparison when you see the response, oxy and deoxyhemoglobin response, and you see slightly larger response during dual task compared to cognitive task serial 7 only. Of course, I pass you the detail. We have to deal with a lot of issue with motion correction. We did not have so many data there, but in parallel, using grants with the National Defense, IDEAS grants with the company MDA and our colleagues from NRC in the Flight Research Laboratory in Ottawa, we developed also this project where we wanted to compare wireless EEG and wide standard EEG NIRS during typical cognitive tasks. And typically the cognitive task we would use during dual task, like typically the end-back task that Karen was mentioning. So again, the end-back task would be to press a button if the letter here is the same as the one placed twice before. That would be end-back 2. And if it's end-back 0, you just press the button when it's 0, when you have the letter. And it's a standard block design, 60 seconds. And we acquire data either a personalized montage with glued optodes targeting bilateral frontal cortex, or using a wireless system from Artemis. And as you can see here, you see the covering we do with personalized montage, and then the covering we would do with a standard commercial device on the cap. Here's an example of few subjects from the sensor data. And what you see is that overall, we get mainly negative response. So decreased deoxyhemoglobin during the cognitive task compared to baseline, nicely reproducible from one to the others. And what we did here is a first preliminary result on some 3D reconstruction. This is work in progress, where you see a slight difference between 0 back and 2 back in this region. And you see the accuracy of our reconstruction over the prefrontal cortex. This is, of course, highly preliminary. In parallel, what we did with a group of capstone students from electrical and computer engineering at Concordia is we looked whether over those data sets, not trying to reconstruct the data, but just looking at the ongoing near signal, if we can use that to predict the workload. And actually, we had 17 participants. Here we are using the wired system. So we have 12 trials of 60 seconds, either 6 of n-back 0, 6 of n-back 2. And we propose machine learning to guess from the data, to predict from the data if we are in n-back 0 or in back 2. So if we are with low or high workload conditions. We use the time to increase our dimensionality. So we'll put local average of our data every 4 seconds. We removed sections with large motion artifacts, and we used 5 features for oxy, 5 features for deoxy. Standard cross-validation scheme, 8% of the data for training, 20 for testing. And what our students found, they tested several machine learning techniques and standard ones, and using random forest, they were able to reach 87% accuracy of prediction of workload. And this is very promising because this is typically a technique that we could use to assess how how the dual task, like single task versus dual task, is evolving in a particular participant before or after a specific training. I just would like to finish that all the tools I presented are available on a software package called Nearstorm, and I will let Karen finish to show what we want to do next through our collaboration.
Thanks, Christophe. So very quickly, we've got a kind of very new collaborative project where we've also added Dr. Marta Kirsten Ortel from the Gina Coady School of Engineering, along with Habib Ben Ali. Apologies, Habib, I somehow have left your name off this screen, but you are definitely involved in this as well. So the general thrust of this program, next slide, please, is to kind of get more into the true to life, getting back to those activities of daily living and try to create a more true to life experimental context. And so we know, I mean, some of what's on this slide is already background. I won't go over it, but really emphatically in this kind of lab-based multitasking assessment, oftentimes we have impoverished testing context in the sense that we don't necessarily have audio and visual information. And we certainly typically in labs, as the picture to the right shows, don't have sort of simulation of the kind of movement and complex scene perception that you might encounter in everyday locomotion. So we wanted to get kind of a virtual reality facility up and running at Perform. So we've partnered together with a team of students supervised by Frédéric Lesage at Montreal Polytechnique to build a library of virtual reality and augmented reality ready cognitive executive function tasks that we can present to our participants. And what the students succeeded in doing is to synchronize this setup so that we could acquire fNIRS data with also the usual metrics for gait analysis, foot switches, electromyography, motion capture, if we like, in addition to behavioral measures of cognitive performance. So here you see somebody walking in our setup, and in the middle screen, you see and you hear the NBAC stimuli now encountered in a simulated walk shown with the augmented reality visor. And on the right, so I think we can stop the audio because I'm talking over the, yeah, thank you. So you can see what it looks like with the Artinus Bright wireless fNIRS cap with the augmented reality visor on top. And the students were very careful to make sure that none of the optodes were disturbed by adding the AR visor. You also see the optimal montage and the 3D reconstruction of the serial sevens task, that subtraction task performed alone versus the dual task condition. So there's some separation evident, just like the images that Christophe showed previously in the HBO and HBR, suggesting more brain activity in prefrontal regions during the dual task condition, as you might expect. So moving forward, we're hoping that our collaboration and this new piece of infrastructure and software that the students put together will enable us to address the following future aims that span basic experimental manipulations of cognitive and motor demands to using fNIRS data to predict multitasking workload using AI, similar to that classification work that Christophe just showed us. And a longer-term objective is to develop virtual reality and augmented reality protocols for training purposes. And the idea here is to preemptively strengthen, to prevent falls and dysmobility, or to improve complex walking abilities in a rehab context with progressive levels of multisensory complexity that we can control within the safe and controlled lab space while we are simulating real world complexity. So in closing, I hope that Christophe and I have given you a sense of our ongoing collaborative work that is generously supported by the Perform Center and done in the Perform Center and where we're headed. Thanks so much for your attention.
So we're now going to take a break for 15 minutes and then we'll rejoin here for another talk.
Hello, so welcome back, everyone. So now we move on to, I guess, the main event for this morning. I'm so very pleased to introduce our keynote speaker for today's session, Dr. Meltem Izzetoglu. She's a faculty member of Electrical and Computer Engineering Department at Villanova University in Pennsylvania. And she's also affiliated with the Saul Corey Department of Neurology at Albert Einstein College of Medicine in Bronx, New York. Dr. Izzetoglu has background in both electrical and biomedical engineering fields, coupled with experience and interest in design, development, and evaluation of highly portable optical brain imaging systems. She's been involved in the translation of 2 near-infrared spectroscopy-based brain imaging devices, going from lab to field and clinical use. Over the last decade, Dr. Izzetoglu has been focusing on the development of wearable bio-optical sensors, physical and digital head models, signal conditioning algorithms, data analytics, and metrics. She has an impressive list of publications numbering over 150, 4 patents with 1 pending. Dr. Izzetoglu is funded by the National Institutes of Health, National Science Foundation, U.S. Department of Defense, U.S. Army Medical Research Material Command, Pennsylvania Department of Community and Economic Development, and the Coulter Foundation. Her projects include the investigation of cognitive control of mobility in young and aging populations, assessment of cognitive enhancement, cognitive decline and expertise development, detection of cerebral hemorrhage and edema development in traumatic brain injury, and monitoring of local tissue oximetry and anesthetic depth. So turning now to the main event, a couple of housekeeping points before we begin. Please feel welcome to add your questions in the Q&A box at the bottom of your Zoom screen, and we'll field all questions from the earlier session today, plus the keynote during the roundtable segment, excuse me, following the keynote presentation. And with that, a warm welcome to our keynote speaker, Dr. Izzetoglu. The floor is yours.
Thank you very much, Dr. Lee. I am honored to be here today. Thank you very much for inviting me. It was wonderful to listen to your talk also. So let me try to make the presentation appear as I want it to appear. Let's see. So today, as Dr. Lee mentioned, I will try to give you an overview of our more than a decade long actually work, past work, present research, and future plans on our studies for the cognitive control of mobility in aging populations.
Sorry, Meltem, I think you're still sharing your presentation view.
How was I doing it? Let me see.
Under the display settings.
Settings. Oh, yes. It's here. All right. Better now.
Perfect.
I like my red dots, so I'm going to get that. Okay. Oh, not that one. Where's my... Okay, now I have it. So I will try to summarize our past work, as I said, present and future plans on today's talk. I tend to kind of get carried away with my research, So I hope I can fit everything that I want to present to you today, given the 45 minutes of my talk. So this is, before diving into our cognitive aging studies, Dr. Lee, during her introduction, actually gave a very nice overview of my research. But I wanted to kind of introduce my lab to you before we dive into the cognitive aging studies that we do in my lab. So my lab focuses on monitoring of human performance and health using brain and body monitoring devices. So main focus though is on neuroimaging applications, focusing on fNIRS. Actually, for the past probably more than 20 years, I have been involved in fNIRS research. So originally when we started, it was more on the technology development and also the algorithm development. Now it's getting more and more established. So a line of my research is still actually in translation of this methodology from bench to bedside and to the field. So in clinics research and also everyday, everywhere research, so that the technology can afford it. I will talk a little bit during my presentation of the current designs that we're working on. By training, I am actually a signal processing person. So my interests also lie in the algorithm development for the processing of fNIRS and other sensors, brain and body monitoring sensors, data processing, algorithm development for feature extraction, actually for first, the artifact removal, and then data conversion and feature extraction, and then actually data fusion and classification. Another line of research that I'm very involved with is in working with head models. And we work on in silico computerized head models, in vitro physical lab phantoms, and also animal models for the healthy and injured head studies. And also there is a breadth of applications that we work on. One of them is cognitive aging. For the past more than a decade, actually, we have been working on cognitive aging. Recently, I'm getting into the driving research, and augmented cognition, enhancement of cognition and cognitive performance has always been an interest. And use of fNIRS in clinical research was also an interest, and we had worked in anesthesia monitoring, so we use the technology in operating room. Eating disorders or social anxiety has also been an interest. Hyperscanning is another one, which I will kind of talk a little bit about that too. And also not just cognitive activity monitoring, but the technology allows physiological monitoring, so injury models and injury monitoring for hematoma, bleeding in the brain, and swelling in the brain, and oximetry studies were also in my within my research portfolio. Obviously, all this work, I'm an engineer. We work closely with clinicians and also psychologists, neuroscientists in collaboration within the region, within the nation, and also globally. And my research has been sponsored by private and public sponsors, funding agencies through several years. So to give a brief overview, again, how I get into the cognitive aging research is, it is probably 12, 13 years ago. My colleague, Dr. Roy Holzer from Albert Einstein College of Medicine has approached actually to our group. Back then, I'm in Villanova University for the past 5 years, but before that, for 15 years, I was a faculty at Drexel University. So Dr. Holzer, who is a professor in Department of Neurology and Psychology Department at Einstein, and also directs the the mobility lab there, he was in need of a technique that he can use to monitor the brain activations during active walking. So because their research was using fMRI, but the studies were conducted during imagined walking. And for the dual tasking, think about it, you imagine walking and on top of it, you imagine that you're doing the dual tasking. So he was interested in looking into other modalities that he can do on the ground, active walking, and simultaneously and continuously monitor brain activation during walking tasks. So he approached us, and it started this most fruitful collaboration that between us. For many years now, we had several NIH R01, 5-year R01 grants, and also, I think 30 plus now joint publications, not including conference even. We have been working on multimodal imaging, not just fNIRS, but also MRI, structural MRI, and connections, functional and structural underpinnings of cognitive control of walking and disease conditions. We primarily worked on dual task walking paradigms, but I will also mention the other task protocols that we have been working on. We looked into healthy aging and also several different age-related disease conditions and populations. Our joint collaborative work expand actually to other collaborations within the nation. We are closely working with collaborators in Urbana-Champaign and University of Illinois at Chicago on our MS studies, and also with other colleagues from different universities. We had actually, Dr. Lee and I was talking about it, in year 2020, Gerontological Society of America's annual meeting, we had organized a session with other colleagues, and we actually also have a very recent consensus guide paper in the use of fNIRS on aging studies. So it was mentioned before in Dr. Lee's and in Dr. Grova's talk that mobility impairments are common in aging, and they are associated with increased risk of falls, disability, and mortality. So when these manifestations of mobility impairments become apparent, they can actually be monitored by using the behavioral outcomes. But what was needed was the neural underpinnings, the cognitive control, the source of those impairments. So neuroimaging research was needed, and to identify those functional brain substrates that subserve mobility in real time. So when we look at the grand scheme of neuroimaging modalities that exist, the way we approach and compare those are based on several different aspects, where fNIRS kind of lies in the middle of all. It has a medium level spatial resolution compared to EEG, it's much better. It has medium level temporal resolution compared to MRI, fMRI, its temporal resolution is better. It's highly portable. It can lend itself to highly portable devices. Wearable and wireless versions exist now through various commercial companies produce highly portable and wireless versions. It's non-invasive, and most of the, compared to specifically MRI machines, it's also very affordable, and it has zero runtime cost. So longitudinal studies can also be performed. Dr. Grova very nicely summarized the technology. It's optics-based, light-based, and within the select wavelength window, which is most of the time referred to as the optical window, tissue becomes transparent to light actually. So we can actually capture some of the light that reflects back without getting fully absorbed. It measures the cognitive activity related hemodynamic changes. Actually, it measures hemodynamic changes, but depending on the tasks that we select and use, the neural activations have manifestations in hemodynamic changes through the neurovascular coupling process, and so that we can identify cognitive activity related changes by monitoring changes in oxygenated hemoglobin and the deoxygenated hemoglobin and related to the cognitive activity at hand. As mentioned, it is safe, non-invasive, portable, wearable, affordable, and another very nice characteristic of it is, compared to MRI and EEG, it's more immune to motion artifacts. It's still a problem, but you don't need to lay down in supine position and stay completely still. So it can be used in upright walking studies, and also facial muscle movement is practically non-existent in fNIRS recordings, unless, of course, you move your eyebrows and move the location of the sensors in the frontal areas. But as I always say to my students teaching in signal processing in my undergraduate and graduate level, there is no one single perfect algorithm or method that is without any problems. So one has to know the disadvantages of the technology too. One of them is actually the penetration depth. By, as Dr. Grova said, like 3 centimeter to about 2.5 to 4.5 or so is actually a good source detector separation that guarantees the depth of the photons or the depth of the light to the tissue, cortical tissue. But if you make the source detector separation too close to each other, you may not reach the cortex, which is most of the time used for superficial layer contribution extraction. Or if you separate them too far, then you will not receive any light. So the signal to noise ratio drops with the source detector separation. So deep brain measurements is not possible with the current existing methods if you stay in the power ranges that are safe. And here is an issue too, but most of the new designs, commercially available designs, now have the fibers and the lenses, so that if you separate the hair correctly, then you can make full head measurements. The applications are growing because of all these advantages that the technology offers. It can be used in everyday, everywhere environments, in the laboratory, outside the laboratory, in the field, in classrooms, in operating rooms, like we used in anesthesia study, in the classroom, like we used in our reading comprehension studies, during driving, simulation or real. Hyperscanning is possible. We used it in mother-baby interaction studies. We used in trainer-trainee monitoring in medical simulations. And we heavily used it in our cognitive activity monitoring studies in aging populations. It's not just us who used it, but very many colleagues all over the world is increasingly using the technology because it allows monitoring of continuous monitoring of cognitive activities during active walking tasks in elderly populations. So they differ in different aspects in terms of populations, some studies compare young and older adults. Some studies involve populations of healthy older adults or several different age-related disease groups. Some are on neurodegenerative diseases like MS, Parkinson's, and others. Some are on age-related diseases, which we also worked on mild cognitive impairments and other comorbidities like diabetes, asthma, and others. The tasks that are being used is also have a wide range. So some include standing tasks for balance. Some include walking tasks on the ground or on treadmill. Some studies include dual task walking compared to single task. Some has uneven surfaces or obstacle negotiation. Some studies looked into running or climbing stairs, and even some studies looked into stimulation outcomes for rehabilitation or intervention outcomes. The brain monitoring with fNIRS also sometimes differs in terms of the use of device. There are different types of instrumentations that exist in fNIRS. Most of the existing studies depend on continuous wave technology, but there are others, which I will kind of briefly talk about them too. Some studies look into, like most of our studies are prefrontal cortex, involvement of prefrontal cortex in cognitive aging and walking studies. Some look in motor areas or full head. Some studies use structural MRI, functional MRI, EEG, and other measures as multimodal approaches so that data fusion can be made, neural activations and hemodynamic activations, or the structural changes can be investigated in terms of how they result in the functional outcomes. And there is also a wide range of data analysis methods that has been applied. In terms of our research, the fNIRS devices, there is now an abundance. When we started 20-something years ago, using the fNIRS technology for cognitive activity and physiological activity monitoring, there were not many devices, commercially available devices that existed. Now there are several different ones. There are primarily three categories that uses different types of instrumentation and engineering. The two of them are called, one like time resolved or time domain technique, and the other one is the frequency domain or intensity modulated technique. Those are excellent in the sense that they provide absolute measurements of HbO2 and Hb. However, with the current technology that exists, the devices are big and they are also on the expensive side. Most of the aging research uses continuous wave, as Dr. Grova also explained. The technology actually sends a constant level of light and looks in the received attenuation in the received light, and using that attenuation, change in the attenuation, change in Hb and HbO2 can be measured. So it's a relative measurement. So there needs to be actually a baseline region that we look at the contrast in the measurements of fNIRS. But the beauty of this technique, it's simple, and it can be engineered as wearable, portable, wireless versions, and several different commercially available devices exist. We used in our studies mostly the fNIRS devices, fNIRS 1100 imager, which is a continuous wave technology again, but it is, there is a technology evolution, but I will not go in detail. The current version is it is a sensor band that has the wiring in a flexible circuit board, and it uses surface mount light sources and detectors. So it's covered with a flexible foam, so it can be used on the forehead like a Band-Aid. Its application is in kind of 2 or 3 minutes it takes, when you make sure that there's no saturation or dark current, no hair underneath, and there's good contact with the skin, you're good to go. So of course, it can only measure it can only be used on the frontal areas, so it can only measure the executive functioning. But we were more interested in our studies on executive function, on the higher level of cortical activation, like executive functioning, attention, working memory, decision-making, problem-solving, all those higher level domains that we were interested to monitor in our studies. So actually the version that we used worked pretty there for our purposes. The sensor has 4 LEDs, and it's also safe, it's not laser. And there are 10 detectors on the sides of it. The source detector separation is 2.5 centimeters. And we actually had a recent publication with my PhD student on this, and showed that 2.5 centimeter reaches the cortex, and also with good signal to noise ratio, which with actually better, as you get closer, your signal to noise ratio increases because there's less absorption, but it reaches the cortex. And with this configuration, we can have 16 channels of recordings, 8 on the left and 8 on the right hemisphere, and it monitors the Brodmann areas of 9, 10, 45, and 46. There is a wireless version too, but it has less channels. So in our aging studies, we used the full forehead 16 channel version. Just wanted to mention that, watch for us. We have been working, when I moved to Villanova, I started working on another design that has now several senior design projects and the manufacturing grant to have everything wireless. All the wireless fNIRS that exist still has wires, and it kind of it defeats the purpose to me. And the movements of the wires can cause noise. So I had this dream of having just one sensor with the Bluetooth and the antenna and all the electronics on it. So you can place it on your head and you can operate it with your phone. So it could be your pocket brain imager for anybody, everybody that can monitor their brain activities anywhere, everywhere, like the smartwatches. You can monitor your brain activity too. So it evolved actually. Now we have a working app, a working sensor, and actually the app can collect the data, analyze the data, even has the cognitive tasks in it. So watch for us. In the near future, it can become a more usable, a more professional version, hopefully. So in our studies, we use, as I said, the 16-channel forehead fNIRS device. And the protocols that we used for our aging studies mainly involved the single and dual task walking paradigms. And also, actually, the studies involved 2 single tasks. One is the single task walk. The other is a single task, an alphabet task that is singly done. And then there's the dual task walk. So during the single task walking, or initially we called it normal walk, then we switched to single task walking. It is walking around an electronic mat at the normal pace for 3 consecutive loops. So a straight walk, turn, back straight walk, turn, another loop, and then another loop. So that was a single task walking. And the electronic mat collected the walk features. And with the fNIRS, we collected the cognitive measures, HB and HBO2. The cognitive task, which is in the dual task, it becomes the interference task. But the cognitive task itself is while standing on one side of the mat and looking directly in front of the wall in front of you, recite the alternate letters of the alphabet for 30 seconds out loud. So if you're given A, you go A, C, E, G, and all that. If you're given B, then B, D, and so on and so forth. In the dual task, the two single tasks, the walking and the alpha task, the cognitive task, is performed at the same time. We ask the individuals to pay equal attention to both. Now, the three tasks are randomized and counterbalanced across participants. One very important aspect is the baseline condition. Because fNIRS, the continuous wave fNIRS that we all use in cognitive aging studies, is a relative measure, there has to be a baseline region. So the selection of the baseline took us some time to decide on what to use for it so that we can look at the contrast that's meaningful. So the baseline condition we use is standing still and counting silently in the head for 10-second baseline. There are different length of baselines used in different studies. We, from 1 second to more, 15 seconds or so. We use a 10-second proximal baseline for each condition. And we measured the activations relative to those local baselines. So in some studies, we looked at the whole task epoch in each task condition. In some studies, we looked at the 6 straight walks and compared the change over time, the time course, the activation levels in HB and HBO2. Later on, we used a burst protocol in our studies, which is the 3 trials of each task condition. So if you start as single task, your randomized order is single task walk, dual task walk, and alpha, you will have once you finish the cycle, a session, you will have 5-minute break, and then in the same order, repeat the whole session again, 5-minute break, and another one. We use this burst protocol to look into learning and practice effects. Dr. Lee mentioned that there is the 23 sessions of learning. We use just 3 kind of sessions, and we actually had seen that I will talk about some changes during these 3 trials of the same protocol, that there was a learning effect too in some populations. And we use the baseline regions in another study for the measurement of balance, posture and balance, and actually individuals with Parkinsonian syndromes, which I will talk about also. So in terms of the data processing, as Dr. Grova said, there are different artifacts, and there have been very many methods that have been developed to identify and remove those artifacts. There can be, these are very easy to identify. Light can saturate if there's no good contact, and ambient light can get into, or the direct light can get into the detectors, or no light can get detected if there's hair underneath the detectors or light sources. Systemic signals can affect the measurements, including heart pulsations and respiration cycles, and also blood pressure related microwaves. superficial layers and cerebral skin blood flow and skull thicknesses can have an effect. But movement artifacts is probably one of the main issues. Even though it's not as pronounced, there is still different types of noise sources that can affect the fNIRS measurements. There could be a sudden drop of baseline change. There could be spiky noise, and there could be slow changes, because if you move the head, blood can move and generate a slow change. It's very actually hard to identify those slow changes compared to spiky noise, which is very visible. There are different methods. Some of those we also worked on and developed, like Kalman and optimum filters. Most of the time, simple frequency selective filters are used because hemodynamic signals occupy a very slow frequency range, up to 0.1 hertz. Because hemodynamic signals evolve slowly, it occupies a slow frequency range, which is well below the heart rate of 1.2 hertz or something. Well below still the respiration rate, around 0.3 hertz, but it can interfere with the Meyer waves. But still, frequency selective filters are used very commonly. Also, different, more sophisticated methods, like based on wavelet analysis and spline filtering, has also been used. We have also used them too. Now, for artifact removal is one aspect in data processing. Another aspect is the conversion. So I'm going to talk about some of our recent studies on these effects. Modified Beer-Lambert law, as Dr. Grova said, you can use the simple matrix inversion and can capture by looking at the change in attenuation. With this simple matrix inversion of a non-singular matrix that you can form, you can extract the changes in HB and HbO2. But there are some parameters that needs to be identified and used in this matrix, which is the molar extinction coefficients. And there are tabulated values, but they're different. There are primarily, I think, 3 tabulated values that we identified, but they're slightly different than each other. There is also this differential path length factor, which adjusts the path length of the photons related to the source detector separation because of the diffusion of light. The path length increases, and it's adjusted with using the differential path length factor together with the source detector separation. But it depends on very many different aspects, age being one, wavelength, the wavelength that you use, and different actually devices use different wavelengths. Still, like 2 below and above the isobestic point, but they implement different wavelengths and different source detector separations. In fact, it also depends on oxygen saturation. There are very many publications, older publications, that report on DPF. So it is a matter of deciding which one to use, because it may have effects on the extracted HB and HbO2. Another signal processing aspect is, once you do the filtering, get rid of the noise and convert the attenuation or optical density or intensity measurements to the hemodynamic changes, then it depends on which features you will extract. Different groups sometimes use different features, and it also is based on the event-related or block designs. The studies we ran are more on the block designs. There was 3 consecutive walking at normal pace, but it's a continuous walking, so it is a block design. But there are some studies with evoked designs, event-related designs. So you show a stimulus, wait for 15-20 seconds so that the hemodynamic response evolves, like this one. And then from this, you can extract different features. But if it's a block design, the repeated and closely spaced stimulus is shown, then the activations, the hemodynamic changes overlap. And then we get this full time trace of data. And then the features that we can extract from it can differ. Actually, the effect of noise can be different on these two also. So there are different features that has been extracted. Average value is one, maximum value is another one, median slope, we use the slope to variance, we use that to evaluate the inter-individual variability. There are frequency domain, complexity domain features that has been used. Skewness and kurtosis also has been recently used. Now, in terms of our recent studies that evaluated the effects of those conversion parameters or filtering parameters, we had started our studies and our data analysis by using certain molar extinction coefficients and certain differential path length factors. And that was it. But in almost all our publications, submissions, manuscript submission, we were getting reviews of like, what if like you are measuring Meyer waves? Why haven't you tried this method or that method? So we actually reanalyzed our data by looking into different sets of molar extinction coefficients, age and wavelength dependent DPF. We were using one value that is for both the wavelengths. Actually, this was, I didn't give that background, but we had the privilege to work with the father of fNIRS, if I may call, Dr. Britton Chance, when he was alive. And at Penn, we had the chance of working with Dr. Chance. So we're very fortunate about it. So many things that came with our interaction with him. So he was using this one single DPF, and we said, okay, if the father says that, and we can use that too. But later on, studies gets published, and they actually came up with this neat formula that relates or extracts the DPF values for different wavelengths and different age groups, incorporating different previously published studies. So we looked at age and wavelength dependent DPF, and also the filter cutoff frequency, because we were using a cutoff frequency before at 0.14 hertz, which was slightly above the Meyer wave range at around 0.1 hertz. So we were being asked, like, what if you are measuring the Meyer waves? So we tested all these different effects distinctly and also all together, and reanalyze our previously analyzed data with those different measures. Forget this busy slide. What we found is there was no difference in the overall study outcomes. There was excellent reliability in looking at interclass correlations, and also the difference in single task walk to dual task walk was preserved. And also the change in HbO2 and HB were in the same direction. So using in our data set of a very homogeneous age group of older adults above the age of 65 years, in our task and our feature of the average value of the task epoch, the results did not change. However, in studies where event-related designs are done, those systemic Meyer waves could affect the maximum value. In our studies, we averaged that. So those little oscillations of the Meyer waves, even if they existed, was averaged out. That's what we are thinking, that it was not affected much. So when there's a small contrast, use of different molar extinction coefficient also didn't result in any difference in our overall study outcomes. But when there were slight changes in HB and HbO2, so if there's a small contrast in event-related designs, caution should be taken. And more importantly, I think whoever uses what values have to be reported in the publications. That's kind of the take on that we mentioned in our studies, in our publication. We also looked into motion artifact removal. Again, we were getting reviews back because we always use low pass filter with, now we adjusted the cutoff frequency to a level that we can suppress the microwaves. But we were asked, like, why not other sophisticated methods like wavelet denoising, which is good for spiky type of noise. If there is a sudden movement, sudden cable movement, let's say, or a sudden change in like movement of the sensor, there could be spiky noise. And wavelet is known, wavelet transformation or wavelet denoising is known to perform really well to suppress such kind of noise. Or the spline filtering, which is another study, it is good to remove these baseline shifts. We have not observed this type of noise actually, because in all our studies with my collaboration with Dr. Holzer, we do blind analysis. So they collect the data. They have this 2 floors of mobility lab, like Dr. was showing. They have all sorts of, the mats, all the subject testing rooms and everything. So they collect the data, and I receive the data and I analyze it blindly. And then I send them the data, and they do the statistical comparison. So there is this blind analysis that's going on. So I always look at the raw data, and we have not had this baseline shifts, but baseline shifts happen if, there are sometimes I review papers, and sometimes I see that there are studies where reading on a book happens. So if there is a movement of the head, there can be a baseline shift. I had seen this type of baseline shift in our ICU patient monitoring within the intensive care units. We collected fNIRS data in prolonged time in comatose patients. So if they change the patient's position, there is definite change in baseline shift because of the pooling of the data. But we haven't seen, so we had not applied these sophisticated methods, but we looked in our data set of 348 individuals. And again, our findings by using simple filtering and also wavelet and also spline filtering methods did not generate any difference. So it was actually, I think, a validation also of the fact that our data did not have too much noise. It doesn't remove the fact that depending on the data that you have, some of these sophisticated methods are truly needed. As I mentioned, we also run animal studies where we insert an injury in the animal, and there is a lot of poking going on, like blood draws and anesthesia insertion, so all sorts of movement on the animal that happens. And we had seen spiky noises, we had seen baseline shifts, and these methods are excellent, but one should take caution in terms of signal analysis. Now, going from the device, the protocol, the analysis, now some applications that we have been working on with my colleague, as I mentioned, Dr. Holzer. who is also a licensed psychologist, a neuropsychologist at Einstein. Our studies, the initial publication we had is from 2011. So 12, 13 years ago, we started, as I mentioned, he visited our lab at Drexel, and we started the collaboration. And everything started with this pilot study. In this pilot study, we used single task walk and dual task walk on the electronic mat, on the ground walking. And we looked into younger and older adults. And there was only 11 young and 11 old adults. And what we had observed was in both groups, there was higher HbO2 in dual task walking compared to a single task walking. And it was expected because dual task walking is a cognitively demanding, more attentionally demanding and cognitively taxing task. So there's more cognitive resources was needed in the prefrontal cortex. And the difference between the older adults and the younger adults were there was attenuated increases in HbO2 from single task walk to dual task walk. And there was reduced gait velocity. That was also expected too. This finding, the increase in HbO2 was lower as compared to the younger individuals, could be related with capacity limitations. But this was a small study, but still we had seen differences. And we had seen actually bilateral differences through the entire frontal cortex. Then using this pilot study, we applied for an NIH R01 and we received it. The initial NIH R01 that we refer to as cognitive CCMA study, cognitive control of mobility in aging, like I used in my talk title. The initial study that was funded by NIH was a longitudinal one. So 500 elderly subjects was monitored the first year, and then over 5 years, every year. There were a subsample where the MRI recordings were also gathered. Then there were follow-up studies that we received, another 5-year R01. Those two are completed. We are now in the 4th year of our NIH R01 study that looks into MS patients in comparison to controls. We also very recently submitted another R01 in aging and in HIV populations. I'm sorry, how much time do I have? I'll continue. I think I have till 11. So I'll go faster. Main findings of this study was we were one of the first ones to show the role of prefrontal cortex in the higher order control of the locomotion. And the findings in the pilot study were reproducible. So there was an increase in dual task walking in the prefrontal areas in HbO2 oxygenation, and as compared to the normal walk, single task walk. And HbO2, we looked at 6 straight walk levels. The increase was maintained in, there was an increase and it was maintained in dual task walk. So those were the main findings. Then we look into different groups of, oh my God. Okay, I'll move very fast. And I will show some of the groups that we looked into, different groups. We looked at the effects of stress and gender, and we found that older men could be more vulnerable because there were differences in men in terms of HbO2 level changes in dual task walking. We looked at cognitive fatigue. In all our studies, like Dr. Lee was saying, we also did a full battery of tests, neuropsychological tests, which included their fatigue levels, their stress, perceived stress levels, and all those. So we looked at the cognitive fatigue in terms of subjective levels of fatigue and also objective from the 6 straight walk levels throughout the course. And we had found differences again at HbO2 levels. There were attenuated increases in HbO2 levels, but not in the stride velocity in the group with the worst subjective fatigue. So most of our studies actually verified and validated the dual task walking, and it can be used to separate and identify the differences of cognitive activations in the prefrontal cortex of older adults of different groups. Because the CCMA study was for 5 years, we looked into over 5 years the cases with falls. Within this 35 months of period, there was 116 falls in 166 older persons. And we had seen that higher levels of prefrontal activation in HbO2 during dual task walk predicted falls where none of the single tasks or the behavioral outcomes had predicted falls. We looked into individuals with fear of falling, and we found that it was associated with higher and inefficient prefrontal activations. So we had seen several times, and we actually relate our findings to this neural inefficiency concept. When there is higher brain activations with similar to worse gait performance, we think that the results are along the line of the neural inefficiency. In the burst trials that we used, we can sometimes see improved neural efficiency after practice. So this is another very interesting study that we looked the time course. In the burst study, we looked at the time course and relate the change during the time course to attention levels. And also in the 3 trial of the repeated trials, we associated with learning. In 83 non-demented participants using the burst protocol, we look at the slopes throughout the time course, and we look at the slopes throughout the 3 trials. And what we had seen was behavioral outcomes declined, the stride velocity declined during the course of dual task walking, but improved over the trials. So there was also a learning effect, and but decline is like maybe there was there was neural inefficiency within the course, because the HbO2 increased during the course with declined stride velocity, but it is the HbO2 declined over repeated trials with improved behavioral outcomes. So actually there was a learning effect. With reduced activations, we could get better behavioral outcomes. Those findings were not existent in the single task walk because it's more of an automatized. There's still cognitive control of it, but it's more of an automatized one. Okay, I will skip this one. We did several multimodal imaging with fNIRS, primarily involving structural MRI. We first started with the co-registration using vitamin E capsules. We co-registered the fNIRS channels locations as we used in the 16-channel sensor. We co-registered them on MNI and telluric coordinates. We also had looked into different structural MRI measures and relate the structural changes, differences to the functional outcomes. So we looked at the whole brain fractional anisotropy, and we had seen that worse white matter integrity was associated with larger increases in prefrontal HbO2 from single task to dual task walk. So it could explain this neural inefficiency that we had seen. We also looked into gray matter volume. In addition to white matter integrity, we looked at the gray matter volume, and the loss in the gray matter volume was associated again with the neural efficiency, the functional outcomes that we had observed in different actually locations, bilateral superior and rostral middle gyri. This is a recent study that we looked also in cortical thickness and neural variability. Thinner cortical thickness was also related to the greater increases in HbO2 levels from single task to dual task walk. This is a study that we almost finalized to submit to a journal. That we looked also into frontostriatal tracts and the whole brain lesion volume. And in comparison to short physical performance battery as the mobility outcome. And mobility disability was associated with reduced fractional anisotropy in different regions, 2 frontostriatal tracts in healthy controls, but not in MS patients. So this is in our NIH study for MS aging. There was double dissociation actually. The fractional isotropy changes were seen in healthy controls, but not in MS patients. And greater whole brain lesion volume was seen in MS patients, but not in healthy controls. So this was actually a very interesting finding. Hopefully we will send it and get it published. If I have time, I will briefly go over the age-related diseases that we looked into, some of them at least. We looked into individuals with Parkinsonian syndromes and also mild Parkinsonian signs. There were differences in Parkinsonian syndrome patients with Parkinsonian syndromes who demonstrated significantly higher prefrontal cortex activations to maintain postural stability. So we actually analyzed that baseline region in our CCMA study for this group of individuals. However, the mild Parkinsonian sign individuals were similar to healthy controls. We looked into individuals with diabetes, and there were differences in terms of the diabetics in the single task alpha related to neural efficiency, and there were also capacity limitations. So let me check the chat. Oh, okay. Okay. So the multiple sclerosis study, also we have published ones, but it's ongoing, and fNIRS outcomes we are about to have been analyzing, but the overall outcomes for statistical tests will be also done very soon. We looked into individuals with mild cognitive impairments. Now I would like to, without going over the other ones, I would like to go into a little bit the current and future studies. This is a pilot study that we run for the recent submission to our NIH R01 grant. We looked into a pilot group of HIV positive women, 11 of only those, and we had seen that they had threefold greater increases in dual task walking performance in cognitive activations as compared to healthy aging cohorts. However, in the BURST trial, we had seen that practice improved neural efficiency in HIV positive women. So that was one of our kind of suggestions, that the BURST protocol can actually, hopefully, be used to improve the walking outcomes. We also started looking into machine learning. We were talking that we are in the era of AI. And I think more and more studies should look into classification of different groups using machine learning methods. So we used our CCMA, large data set from CCMA. We started with the task classification first, because dual task walking is a cognitively demanding, more higher workload condition. If we can separate those two, first we looked into that, and we used deep learning algorithms, and we reached like good classification levels in the training set, and almost perfect classification in the training set. The next is the disease, because as I have kind of tried to go over, we have various disease data sets. So we can use it for separation classification purposes. Another area that I'm very interested in to move into is driving, the other mobility. Walking is one mobility condition for older adults, but driving is the second one. So I am very interested in going into the driving research in older population. We run a study with my colleague in civil engineering who has a driving simulator, and we looked into distracted driving, dual task driving in younger population. And we had applied the machine learning to it too, to fNIRS data. We reached very high accuracy in that. In aging population, the next step is to collect data from older adults and during driving, distracted and single task driving, and look into the machine learning aspects of it. I'm very sorry I'm over. I would like to thank again for giving me the opportunity to talk about my research. Thank you very much.
Thank you. So now we have some time for some questions. Just a reminder to everyone to please enter your questions using the Q&A feature at the bottom of your screen. We do have a couple questions that were entered during Dr. Grova and Dr. Lee's talk. These are from Melody McGrath. The first question is, sleep and procedural memory studies have reported that improvements in motor skills have been associated with non-rapid eye movement sleep, non-REM. More specifically, certain brain oscillations, sleep spindles. Do you think that looking at sleep stages, quality and oscillation may be of benefit in improved mobility?
So maybe I can address that one. Thank you for the question, Melody. So my understanding of sleep spindles and memory consolidation is non-expert. However, from what I understand of your question and what I've heard over the years in the sleep lab and the kind of results that have come out, I guess it would depend on what is being assessed in terms of mobility. So in terms of motor skill learning, and memory consolidation through a good night of sleep. We also have shown, and coincidentally, it was Sarah Fraser, who is also mentioned in Dr. Izzetoglu's talk as collaborator, when she did her PhD with us at Concordia. She did look at memory consolidation over a night of sleep in fine motor learning. So in terms of gross motor performance and mobility, I would say that, much depends on the brain regions that are hypothesized to be affected by this kind of memory consolidation. And my guess is that the research is really focusing on hippocampal regions or parahippocampal regions. And so in terms of aging and motor control or cognitive control of walking, more specifically, may not necessarily affect the same specific brain regions. However, if there was some kind of memory task that was paired with the mobility performance, like in a dual task memorizing paradigm, then there might be some more implication of sleep quality.
Okay, we have one more question. Does this technique, EEG or NIRS, also consider both local and overlapping brain regions?
I will try to get this one. I'm not sure I understand the questions. I will give different answers. Yeah, we can combine EEG and NIRS, and they are complementary. That's one thing. I mentioned overlapping regions, which is locally overlapping region in my talk. So you can have different source and detectors that are trying to reach the same regions. It's like having different sensors, like in EEG, catching the same kind of activity. And that's actually very useful when you want to do 3D reconstruction. If you have a sparse montage with very low density, then the 3D reconstruction would just be, you don't really reconstruct, you mainly project the data on the cortex. So that would be one thing, but in NIRS, usually it's a kind of trade-off. So either you might want to analyze very accurately one local regions and then you densely try to map that one, or you want to more have a whole brain representation, then it's going to be more sparse because of the current technology we have. There have been some techniques using very large high density montage, but they are not used in clinical practice for the moment. They are mainly research. I don't know if perhaps Dr. Izzetoglu want to comment on that.
If I may add, I think it is also related to EEG's source localization too, because it's lacking spatial resolution. So some activations from deep brain could be reflected on the measurement area still that is coinciding with the fNIRS. So it's also related to if you can localize EEG activities, and then you can, I think, look into the same regions that fNIRS is measuring, if they're coinciding, and also temporally, it's another good problem to have, because EEG provides these fast activations, which in fNIRS we can see its manifestations in terms of HB and HbO2, how the neurovascular coupling, if it's intact or not. Actually, those kind of studies, if you ask me, should be carried on. Most of the time we look into, when we talk about data fusion with fNIRS EEG, we extract features from fNIRS, features from EEG, and then we use them in statistical comparisons or in machine learning algorithms. There is a dynamic relationship that gets lost, actually, from the starting neural activations to its manifestations in HB and HbO, the hemodynamic response. That can actually be investigated, and more features can be extracted looking at combined features, if you ask me, temporally and also locally.
Thank you. We have another question from Habib Ben Ali. Motor learning involves subcortical regions. fNIRS does not have access to these regions. Does this imply that dual task motor learning using NIRS is limited? Anyone?
In terms of, if I may, in terms of deep, like below the cortical level, yes, it currently has that drawback that it cannot. So some of the studies that we always look into specifically with the fNIRS that we have, the frontal, we're limited into other, but I know that you use Artemis device and there's the NIRX one full head versions. So that covers the cortical areas through the whole brain, but still the depth is an issue at this point. We can only look into their manifestation if there is a front cortical, associations. That's all we can measure at this point.
I would add, especially in terms of wearable, like if you want to do tasks like while moving, the main two modalities that we have for the moment are EEG or fNIRS, and none of them are actually sensitive to deep structure for the moment. So we have no solution to monitor deep structure in realistic movement like the task we are proposing here. So we have to look for the how those cortical regions are connected to the prefrontal cortex, and that's the manifestations we can measure, and they make sense. And the relationship between prefrontal cortex and deep structures during learning have been shown in other modalities like fMRI that can reach those regions. So that's an indirect way, but not directly the deep structure for sure.
Perfect. So we don't have any more questions. We can give a, oh, you have one more question?
Yes.
All right.
Perhaps I would like to have one for Dr. Izzetoglu. So thanks a lot for the great talk and lots of data there. And I was wondering in general, like if you can comment on intra or between subject variability, and in terms of like, I'm coming from epilepsy or single finger tapping, where it's relatively, we get very nice response. We show we have a response. In those tasks, the design we have is usually we don't have that many trials. So in terms of average evoked response at the single subject level, the signals to noise is quite low. We've been showing negative response, sometimes positive, it's varying. So how do you cope with that in your general research? Is it like by having a lot of subjects that you get the main trends, or are you able to get some trends on the single subject? How variable it is? I wanted to get a little bit the more practical aspect behind that, because and which is also impacting the design, like how many trials when we do such design.
Excellent question with no simple single answer. I think inter-individual, like inter and intra individual variability is an issue in all neuroimaging studies. It's really not like, how can I say, like heart rate, it's within a certain range and you're okay. Now, there are changes in cognitive response and cognitive performance related with sleep, related with what you had eaten, what you had drank. Did you have caffeinated drinks or not? Depending on your mood that day, your cycle, what's that? There's a word for it, biological chronobiology, right? So anything and everything within one person can change. If you make the measurements morning or afternoon, you may get different results, let alone a large group with. So that's absolutely right that we go with very many, if possible, individuals. And we also, within session though, we don't do like different days, different, who can afford that? It's tough to run longitudinal studies and collect that many data. Actually, I had thought of, like Colin, why don't we collect data? I was thinking like I can collect data from myself forever, every day, morning and afternoon. So I have a database of like how it changes, for me at least, right? But in a scientific study like we run, we are bound to have a certain number of individuals to get tested. And those studies are extremely expensive, also time consuming and expensive. The NIH studies that we have for 5 years, it involved 12 graduate students, and the whole budget was actually for subject recruitment and bringing them, specifically vulnerable groups like aging individuals. Dr. Holzer, they run vans to bring the patients, to bring them back home and all that. So you are limited, actually. That's why this open source data can be extremely, it can take the science to another level if we can all share our data that we collect. So there is no simple answer, like how many subjects. We do power analysis, and then we hope that it holds. How many trials? It also comes by trial and error. When we started, the length of the single task of how long should it be? How long should the baseline be? So it comes, I think, if the outcomes are reproducible, that gives you, like, yourself and others can reproduce it, that you are on target, you feel like you did the right thing. So it's kind of a little bit trial and error at this point, but we're getting there. There are so many studies using walking tasks now, different groups, and we all converge and find kind of similar, comparable results. So there's hope, but single trial, that's why also maybe AI can add. Multimodal definitely will add, and AI can add too. But I'm sorry, I don't have the single short answer to your question, but it's a good problem, so we can keep working.
Mm-hmm.
Well, thank you very much. So does anyone else have any other questions? Again, to the audience, feel free to enter them in the Q&A section at the bottom of the screen.
I might have a last one, if I may. We'll do it quickly. You mentioned, of course, motion artifacts, which is a main thing. If we could, and I was wondering if you did a bit of statistics when you do those different tasks. Because we're a bit surprised in our case, like you do a dual task, you do a single walking task, or you do just a cognitive task. Like, would you have when we have more chance to see the motions? Do you have you checked about that? Like when, like, is the motion occurring similarly in all conditions, or is it more in one conditions compared to the others? Or like, what's your experience on that?
Definitely the walking condition, single or dual. But the way our setup was, it's still a wired sensor, right? They wear this. There's a long wire at the end, which is connected to a how can I say, curtain rod kind of something.
Yeah, we have the same. Yeah.
You know that you have the same. So obviously the cables can move. Sometimes they can get stuck in the, so it generated some, but when we looked, we eliminated the data that is completely not usable. Excessive noise, saturation, or dark current because of any contact loss or pull of the cables and everything, which was around 3-4% of the data, by the way. I think, to me, this is a feeling that I have, but I am kind of in the process of getting a fNIRS device. Their fNIRS EEG wireless version. So I can actually pinpoint this feeling more, but I think with the fibers, the contact loss can happen more frequently. With what we have, it's really when you put it, and if it's tight enough, it doesn't really move much. But with the fibers, I think they may move and generate more noise. That's my thinking of things. So definitely walking generates movement. Talking, we had run studies, different studies, like giving a speech for social anxiety, speaking anxiety. No artifacts there. We had other like talking related ones, no artifacts there either. But walking generated sometimes some artifacts if the sensor was not placed in good contact and moved. And also, Dr. Holzer's lab moved one time from one location to the other. And at the time when they moved there, there was a distinct noise that was coming from the light bulb, I think. That was on one corner of the room. When they walked towards that, the data increased. When they walked backwards, the data decreased. So we solved the issue later on. So there are still different things that we need to consider, but some of them are, of course, like I think one should avoid garbage in, garbage out, right? The data should be collected first very carefully so that you avoid all types of noise that you can. But the remaining, my main concern, okay, do we have time? Because I can talk of my experience in things. Some algorithms on their own also can generate algorithmic noise. The wavelet denoising method that we used, we ran a study actually. Everybody publishes Dobish's 5, level 5, right? Why? We tried different ones and we tried different levels. Actually, if you reduce the levels too much, then you corrupt the signal. You do not remove the noise, but you corrupt it actually. So algorithmically, one should be also very careful in removing. Another concern for me personally is if there is a contact loss, and if you remove the spiky noise, how are you sure that the remaining is coming from the brain? Yes, you can make it look smooth, but is it from the brain itself if it completely lost the contact? So those are things one should be very careful about. So that's why I was saying consensus guides are good, set algorithms are good, but it's still a very much open field actually for more development for algorithms that can better identify and remove the noise. It's still ongoing. I mean, EKG is ongoing, right? Yeah. The heart rate variability is ongoing for 100 years. So we are new, but it's those are good problems to have, I'm saying. We have a lot of work to do.
Okay, thank you.
Sure.
So we have one last question. So this is for Karen. Dual task involves interference between the two tasks. What is the effect of this interference in elderly? Is it positive or negative effect?
Okay, well, the short answer is it depends. The kind of classical pattern of data behaviorally is that when you compare single task performance to dual task performance in two age groups, namely young adults and older adults, then the magnitude of the cost, that is performance decrement, tends to be larger in older adults. But I say it depends because in some cases there is evidence of either no cost, maybe suggesting automaticity of functioning of one of the component tasks, or sometimes facilitation. And so it's not a straightforward equation. It seems to be maybe a curvilinear relationship. So there were some publications maybe over 10 years ago by now from the Max Planck group in Berlin, suggesting that with very simple cognitive tasks that simply require, simple reaction time for tone detection and whatnot, that can actually be facilitative compared to single task walking and single task balancing. And the idea there is that if you ask people to pay full attention to their balancing or walking, it's rather unnatural. So it kind of de-automatizes motor performance in an unnatural way, thus disrupting motor performance. But actually there's a study that my PhD student, Avril Parker, has carried out in another part of the Perform Center space on overground walking and manipulation of a whole range of cognitive complexity and this kind of auditory pacing. And at a simple level, the auditory pacer stimulus seems to be facilitative in terms of improving the cadence and the regularity of cadence of walking. But as you increase the complexity and cognitive demand of the task, then you start to get interference and performance decrement. And it does seem to follow that kind of curvilinear shape that the Berlin group has reported before. So yeah, it really does depend on the type of cognitive demand that is paired with the motor task. But thanks for the question.
May I ask a related one?
Mm-hmm.
How did you decide you're using one back and two back? The reason I'm asking this is we always used this reciting the alphabet, skipping one letter. It actually generates an activation in the prefrontal cortex. Mm-hmm. I use the same in the driving one with the young adults. The alphabet task didn't generate much on the frontal cortex. We also used the serial 3. Mm-hmm. It also didn't generate anything for them. Actually, it didn't generate, it's very strange, but those were engineering students. Maybe that was the reason, I don't know. But it didn't generate the dual task effect that we were after too. But the alphabet in the young adults generated the dual task effect. There was a huge activation in the dual task compared to a single task driving and compared to the alphabet task. So how can you decide? And also I did myself, one back, two back, and three back. Three back is impossible to do for me. I don't know, maybe I'm getting into the older adult group. No. But how did you decide that it will not overpower and that the dual task effect is there?
Yeah, through pilot testing, basically. So part of it depends on which motor task is being paired. Is it usual walking? Is it faster than usual walking? Is it postural recovery where there's an unexpected platform movement? Is it just basic standing balance on 2 feet or with eyes closed? So I think it's really through pilot testing that we have arrived at those levels. And, sometimes it depends on participant characteristics. So when we introduce, older adults who have other premorbid conditions like hearing impairment, for example, or other, some of the work we've done has been with MCI patients, for example, then we have to kind of dial back the cognitive demands. And, so that's one strategy. Another strategy, apart from pilot testing and just kind of trying to find that sweet spot, is actually to individualize the level of cognitive difficulty. And it's quite a laborious process. It goes beyond pilot testing, but if you have a time for a pre-test session, one can systematically increase and decrease with the staircase method, the rate of presentation of your stimuli. And if you do that with an externally paced task, then you can find the presentation rate that will get each participant to, like, sometimes the target accuracy rate is 80% or 75%. So if you go around between 70 and 80% accuracy, that gives you room to move. It gives you room to see performance decrement And also, you're not at ceiling performance from the beginning with a single task itself. So that is much more laborious. But yeah, I think it's really, there's no magic formula. It's really, it depends on the combination of tasks that you're trying to pair and the participant characteristics.
Okay, great. So I think we're at time now, but I want to thank all of our speakers for joining us today, for your wonderful talks, and to all of our attendees. So we have a bit of a lunch break, and for those that are able to join, we have some student poster presentations that will start at 1 o'clock today. Thank you, everyone.
Thank
Thank you very much.
Have a
Bye-bye.
good afternoon.
Bye.
Bye-bye.
Bye.